Welcome to part 2 of topic 2 for this week, week 4. So we've already talked about how some types of rocks, particularly sedimentary rocks, are deposited in these broad, flat layers that extend over great distances sometimes. An important part of understanding the stratigraphy of rocks, particularly sedimentary rocks, is understanding how they can deform and bend. So in certain circumstances, such as those associated with continental collisions, we get compressional stress, thrust faults or reverse faults, and importantly, folds, where the rocks are actually bent under their own weight and the compression of tectonic forcing. On this slide, I've got a couple of different folds. I've got a simple symmetrical fold here of just some layers that have been bent into an arch shape. These are associated with compressional stress, as are shallow angle reverse faults, also called thrust faults, which can push land up and over itself. Associated with this process of thrusting is also folding of the overlying rocks in the hanging wall. There are two primary types of folds, synclines and anticlines. A syncline is a smiley face shaped fold, so that it goes down, and an anticline is the opposite, so it folds up. It's anti, it's a frowny face. Any fold will occur along an axis, which is called the axial plane. This is the direction along which compression has been greatest. We can see down in the lower left that the compressive force has pushed either end of this block of material together and created these folds. You can replicate this yourself with a piece of paper on a table and pushing in on the outer edges of it. This will give you folds in your sheet of paper. Rocks do exactly the same sort of thing on a broad scale and on a small scale. This outcrop scale fold in New Jersey in the northern Appalachian Mountains shows a moderate scale fold. This is what it looks like when you cut one of these folds in half. As you remember from part 1 of this lecture, some rocks are harder to erode than others, like a sandstone being harder to erode than a siltstone. So these harder rocks tend to protrude from the surface as ridges over time as erosion removes the overlying stratigraphy. On the top left here we have an anticline and upwards fold both before and after erosion. In the lower right you can see this color-coded by age. Up on top of this lower right diagram, we can see that the oldest rocks, the oldest exposed bedrock is exposed in the center of an anticline or upward fold, and the youngest on the limbs of the fold, or the sides of the fold. A syncline is exactly the opposite, where it has the youngest rocks in the center and the oldest rocks on the limbs. Now recall from when we talked about fault planes that any planar feature, such as a planar bedded sedimentary rock, or the limbs of a fold or a fault plane, has both a strike and a dip. The strike is the direction of a line made by the intersection of a tilted layer or fault and horizontal. That's your direction that it's pointing. The dip is the angle between your horizontal and the top of a tilted layer or fault. This has a number of degrees and a direction that it is tilting toward. We defined the strike and dip for the limb of a fold at any location, but not for the entire limb, because the dip of your fold limb is going to be constantly changing, because it's round. The dip direction is going to be oriented 90 degrees to the strike, or direction of your fold axis. While a simple fold is pretty easy to understand, it gets more complicated when you introduce plunge. A plunging fold is a fold that is tilted at an angle. That is, your fold axis is going to be tilted off of horizontal. That's called the angle of plunge. After erosion, your rock layers will form a rounded or V-shaped outcrop pattern. Compare that with the parallel outcrop pattern of a non-plunging anticline here on the right. Here's a real-world example of a plunging anticline. This is an upward fold of some sedimentary rocks in Dinosaur National Monument, right on the border of Utah and Colorado. We are looking directly down the main axis of the fold. we can see that it is a plunging axis because these orange outcrop patterns in the bottom half of this image form a rounded or V shape around the axis of this fold. If I go to another angle of this is the exact opposite direction looking down the angle of plunge, we can see that it forms that same rounded U shape. Now that the softer orange rocks have been eroded away from this anticline, we can see that same rounded pattern when looking the opposite direction down this fold. It also makes it clearer to see the rounded shape of the more resistant rock that is at the core of this anticline, which, remember, is the oldest rock. The oldest rock is at the highest central part of this fold, and the younger rocks are on the limbs or exterior of this fold. If we look at this same fold from the side, we can see the plunge angle. It's about, I estimated at about 20 degrees off of horizontal, that this fold is plunging into the earth. So this fold continues down underground underneath where it is buried. But because of the amount of erosion that has occurred, we can only see the uppermost part of it, including this hard resistant sandstone layer that forms the rounded sort of whaleback shape of this anticline fold. Folds are not always rounded. Sometimes they can be very sharp. These are called chevron folds, and they occur shallower in the ground surface. A nice rounded fold requires some confining pressure of overlying rocks, but when you don't have that, when you're closer to the surface, your rocks will break at angles rather than in folds. So starting with our anticline, we have an upward fold. This purple rock layer is the oldest one that is exposed at the surface, and it is at the center of this anticline feature. The syncline, on the other hand, has the white layer, the uppermost and youngest layer at the center of the fold structure, and the oldest rocks on its limbs. You can get a whole series of anticlines and synclines next to each other, and you can also tilt those anticlines and synclines to produce these funky, wavy shapes in your outcrop pattern. Fold geometry is a complicated field, but simply put, there are both symmetrical folds and asymmetrical folds. If you compress a fold enough, or with increasing compressive stress, you can bend your fold to be asymmetrical, or you can bend it even more to be overturned. This means some of your rocks are actually upside down. If we draw a straight line down from this overturned fold, we encounter the stratigraphy in reverse. If you draw a line through your overturned fold and you go down from that line, you encounter your stratigraphy in reverse, and in fact it repeats a little bit. We can see some of these brittle, more surface-level folds here in the lower portion, where we have box folds where rocks get compressed and form sort of a box-looking feature, a fault bend fold or fault propagation fold that you find at the end of a propagating reverse fault, so you get these very sharp angles. And over here on the right you have a chevron fold, which is a sharp zigzagging pattern that you only find in shallow depths in very high compression environments. Here's a real-world example from Death Valley. We can see this orange layer as a folded rock. This is a recumbent fold, which is an overturned fold that has gone beyond overturned and is laying down on its side. I'm going to draw in some lines showing the different bedding planes of this very ancient sedimentary rock sequence. So we have the older rock on the left, then that yellow-orange layer gets bent and folds over. So it's now underneath the older rock as you go further to the north in this image, or towards the top. And then this other brown layer has been overturned beneath that as well. So this brown layer is actually above younger material. So these rocks are upside down because the fold has gone so far that it is laid down over on its side and been thrust over the landscape at the time. This diagram at the lower right should show this geometry a little bit more clearly. The real-world examples are rarely as nice as the diagram schematic versions. There's one final type of fold we need to discuss, and that is a monocline. A monocline is a one-sided fold, basically a stair-step inflection of layers over some underlying uneven structure, such as over a blind thrust fault. A blind fault is any fault that doesn't reach the surface. If you look on the left, the bottom two examples are two blind faults. On the lower middle, we have a blind normal fault, and on the bottom we have a blind thrust fault, creating that stair-step, single-sided fold sort of inflection in your rock layers. At the top, we have an example of a one-sided monocline fold in the Bighorn Range of the Rocky Mountains. Domes and basins are three-dimensional upwarping and downwarpings, three-dimensional folds, that is. After erosion of your dome or basin, your rock layers will form rings on the surface, with the oldest layers in the center of a dome and the youngest layers in the center of a basin. Two important basins and domes in the United States are the Black Hills of South Dakota, where we have ancient crystalline rocks of the middle crust having been domed and uplifted upwards. This creates an ancient core of old schist, metamorphic rock, and granite igneous rock surrounded by younger limestone rocks and even younger sandstone rocks surrounding it. An example of a basin, on the other hand, is the Michigan Basin in Michigan, where we have the youngest rocks at the center of the basin. They are sedimentary rocks, and the oldest rocks, which are igneous, metamorphic, and sedimentary rocks, around the perimeter of that. You can see very clearly that this basin has nice concentric rings of rock layers of different ages. These two sideways views or cross-sections of these dome and basins can be seen at the bottom of this slide. So now we're going to talk about Capitol Reef National Park in Utah. Capitol Reef is the largest national park in Utah in the south-central portion of the state on the Colorado Plateau. Its geology is defined by a large monocline fold called the Water Pocket Fold, which you can see here on the top of this slide. This fold makes a band of cliffs that the pioneers called a reef, and it also includes a bunch of dome-shaped rocks, which reminded these same pioneers of the Capitol building dome. You can see the Navajo Dome down here in the lower part of this slide, one of these rock domes that lent its name to the Capitol Reef area. This is an aerial view showing the Water Pocket Fold from an angle. It shares its geology to much of the rest of the Colorado Plateau. You may recall the Entrada sandstone from Arches National Park, though it's also seen in Canyonlands National Park. The largest rock formation in this picture is the Navajo Sandstone, a very famous formation that is also found in Zion, that makes up the bulk of Zion National Park. This cross-section sideways view of the Water Pocket Fold shows just exactly how it looks. The compression force has created a blind thrust fault somewhere deep underground that never reached the surface. This caused an area of uplift and folding directly over that fault, and the planar sedimentary rocks were simply deformed as a result of this uplift. By looking at this, we can see that from the upper part of the fold, the western side of the fold, a significant amount of rock has been removed by erosion. This same erosion has removed the central part of this monocline fold and revealed the oldest rocks at its center. In this location, that is the Kaibab Formation, which is the youngest rock at the top of the Grand Canyon. We can see the Entrada sandstone is exposed in the eastern limb of this monocline fold. Because it's farther away from the center, that means it has to be younger than the Kaibab Formation and the Moenkopi and the Chinle and these other formations that are exposed in the center of this fold. Here's an aerial view, again from Google Earth, showing how these different rock layers are tilted. We can see the Navajo Sandstone, which is this white and orange formation, is actually folded and tilted over this fold. And over here where the ground surface is a little bit lower because the rocks, softer overlying rocks, have been removed by erosion, we can see that they are tilting steeply, but the dip of these rocks gets less and less the farther away from this fold you get. Now I'm going to transfer to Google Earth and show you a little bit better about how this looks. So this is a Google Earth view of Capitol Reef National Park. We can see the tilted rock layers present in the Water Pocket Fold. This fold is over 100 miles long, so the national park is very long and skinny. Here in the northern part of the fold, we can see how the overlying Navajo sandstone, this big white rock outcrop, the Navajo sandstone, is tilted a lot less than it is further south along the fold, such as right here, where it can be seen dipping very steeply. These softer overlying rocks dip less and less the farther away you get from the fold, to being nearly flat, such as over here at the southeast edge of the national park. You can see this fold really clearly from the sky because that white Navajo sandstone produces a nice visual marker in the landscape. And we can see that it is tilted a lot less, making the band appear wider or thicker up here in the northern section of the park. It is dipping the steepest, showing just the actual thickness of the rock in the central area of the national park. And then at the southern end, where the fold tapers out, it gets a little less tilted once again. So it goes from least tilted at the ends of the fold to most tilted at the center of the fold. And that is similar to how folds act throughout everywhere, really. All kinds of folds sort of taper out to being the least folded or tilted at their ends, and being the most folded in the central part of the fold. That's all about folds and soft sedimentary rocks. That is the end of Lecture 2 for Week 4.